Welcome. The title of today's notes worksheet is Hyperbolas Day 1. We will explore hyperbolas in the same way that we've done the other conic sections. We'll take a look at the geometry parts first and then go ahead and transition into some of the algebraic modeling. So why don't we go ahead and dive right in with a nice little investigation. First and foremost though, before I do forget, did paste one more drawing in for you on what it would look like. So this is the one that requires the two cones, one on top of the other here. And it looks like our plane is going to divide the cone. I guess it's going to come in perpendicular to the base of the cone. I guess that's the best way to describe it. And it hits the cone up here and forms one branch of an open-ended curve. And then down here is the second branch of the open-ended curve. And the nature of the curve, the bend of the curve, is different than the parabola. In this case, we get what's called our hyperbola. So we'll go ahead and take a look at that piece and sort of take a look at the modeling that goes behind it as well. Why don't we go ahead and see if we can come up with a nice definition for this. As I've done in the past, I've kind of pasted two branches of a hyperbola on your paper, and I would love for you to get a ruler and try to pull this off if you could. So let me read what I have, and then let's get rolling. So it says, the diagram shows the shape of a hyperbola. Measure the distances to the nearest millimeter and complete the table. So I picked just 7 points, it looked like, on that hyperbola there, and I'll have to go to my next screen. And what I'm going to ask you to do, of course, is pick, you don't have to do all 7, to be honest. I would go with at least 3 or 4, though, and then pick any 3 or 4 of these, and then measure the distance to the first focus. Obviously, that's this piece right here. And then measure the distance to the second focus. That's this piece right here. And in the third column, everybody, will be basically what you're going to do is subtract. And so you're going to take the first distance minus the second distance there, but just make sure it turns out positive. The easiest way to do that is to just do it as the larger one minus the smaller one. So whichever is the larger of the two, just subtract the smaller one. That's all. So if you get an opportunity, and I'm going to just go ahead and quickly transition here, just if you're not sure what to do, so pick a point on the hyperbola and measure the distance as accurately as possible to that first focus. Then measure the distance from that same point to the second focus. So again, if you can do that for any 3 or 4 while I'm rambling up here, or you can pause the video and do it, totally your call. And then as you're going to see, obviously, what you're going to do is subtraction here. Just take the larger one minus the smaller one to ensure that it's positive. Theoretically, it doesn't matter as long as you take the absolute value, but that's an easy way around it. So again, and then I'll just kind of highlight 1 or 2 things up here. So if I have my second point, there's the distance to the first focus. There, of course, is the distance to the second focus. And again, you would take the bigger one minus the smaller one and so forth. So if you could do that for at least 3 or 4, I would greatly appreciate it. And then let's see what kind of conclusion you can draw. So numbers here, grab your calculator and subtract them. Now I'm hoping, and again, if you're not done just yet, maybe pause the video as we'll go ahead and put our conclusion in place. But the bottom line here is what you hopefully saw is when you took those two distances and you subtracted them, no matter where you are on the hyperbola, the distances are the same. So I'm hoping you did that. Hopefully you didn't shortchange it too much there, but something along those lines. Those distances are going to be the same. I should say the difference of the distances would be the same. Okay, and so that's going to lead into our definition, which we're going to go ahead and put right down here. Might as well get that going. And then I have my Sketchpad program all queued up here, so I'll show that to you as well. Again, I think the phrase I've been using is from a more dynamic perspective. All right, so here's what I have. The last of our 4 conics. Here's the definition. Notice it starts out the same way. Please remember you are responsible for all 4 definitions. So it's the set of all points in a plane, just like the other 3. And then here's what I have. This is a little flowery, but it works, such that the absolute value, and that's kind of what you did there when you did the subtraction, so the absolute value of the differences of the distance from two given points, and of course, everyone, you know our two given points are going to be called the foci. So from two given points is constant. And that's the idea. The difference of the distances is constant. If you remember when we did ellipses, the sum of the distances was constant to those two fixed points. Great. Now I'm going to do just a touch of quick erasing up here. We're going to be doing a lot of work inside this hyperbola here today, so kind of clear that out a little bit just in case. There we go. That looks good. And again, feel free to drop your pencils for just about 60 seconds or such. And let's see it in action. Here's what I have. And there's our definition right up here for the hyperbola. And here's the idea. I'm going to have from my point to the first focus, that's one distance. Point to the second focus, that's the second distance, and it's going to take the larger one minus the smaller one, so the difference is between the two. And just this string right here is just going to have the difference be 8. I could adjust this a little bit and change that, but I'm going to leave it, that's fine. And when it says collect locus, what it means is collect all the points in the plane that fit that definition. And you can see one branch over here, it's kind of slowing down, but it'll pick up. There's one branch, and there's the second branch. So two branches of our open-ended curve and called a hyperbola. That looks great. Notice over here, those distances are changing, but notice the difference is constant. And when we take the set of all points in a plane that fit that definition, it forms two branches of our hyperbola. All right, I hope that works for you. Kind of cool to see. I like that piece. I'm going to go ahead and stop that. Maybe come back to it in the near future, but let's kind of get the ball rolling on our next piece. So we've got our definitions in place, and it's time to go ahead and transition and see that geometry sort of modeled on the coordinate plane. So we will kind of do the same setup as the last few conic sections. We'll start with the most basic model. In this case, everybody, the model will be with the center at the origin. If you get a chance, can you box that up for me? And I guess the way it's going to be described is that there are two types of hyperbolas that we're going to investigate. One where the branches open horizontally from each vertex, so opening to the right and to the left. That would be a horizontal hyperbola. And also hyperbolas that open vertically, so either up from the vertex and down from the vertex. So unlike a parabola, of course, it's not an either or, it's an and. So left and right, and up and down. So those are the two we're going to see. We've got a few things labeled in there, but you can ignore that for the time being. Obviously, the notes worksheet will hopefully help us fill in all the information that's needed. Well, let's go for it. Let's just kind of read what's on your paper. And again, the great thing about these notes worksheets is you don't have to copy it all down. We can just play a little fill in the blank and hopefully really learn all the geometry and algebra that goes together. Here we go. The distance from the center to each vertex. You've seen this before. Center, vertex. What letter is that in an ellipse? It's A. And it stays as A in a hyperbola. So that's great. Center to vertex. Good word association there. Just good mental association with that. As soon as you hear the word vertex, you're thinking A. All right, great. The line segment that passes through the center and has two endpoints on the vertices is what's called the transverse axis. So if you remember in an ellipse, we talked about major axis and minor axis. This one right here would be analogous to the major axis. And in fact, it just happens to be labeled in the two diagrams that I put here. Basically, vertex to vertex, everybody. Transverse axis. Same here, vertex to vertex. Transverse axis, excuse me. So you could see it could either be horizontal for the horizontal hyperbola, or it can be vertical for the vertical hyperbola. Okay, good. The distance from the center to each focus, there's our key right there, center to focus, just like an ellipse, is going to be labeled as C. So you can see that right here. You know, from the origin, center to vertex is A, so there's your A value. Center to focus is C, so there's your C value popping up on the coordinate plane, and we'll definitely refer to that as we go through the process today. Looks good. Okay, I'm going to go to my next screen, And we have one big piece to take care of. Actually, it looks like two of them, but two investigations to get us thinking about this. So let's follow the directions fairly carefully. Here we go. Number one, draw two asymptotes for the two branches of the hyperbola. Okay, so one of the characteristics of a hyperbola is that their branches approach these lines on the coordinate plane, essentially. They approach asymptotes. We've seen this before when we talked about rational functions, and now we're seeing it on the coordinate plane for any hyperbola. So you can kind of get a sense of this. This is going to go right through the origin there, and as best as you can, let's go ahead and get the boundary lines for the branches, for really the arms on each branch, I should say, of these hyperbolas. There would be one right there, and you can kind of see the way the curve is bent. It's going further out. It's going further out, but there is a boundary to that arm of this branch right up there. Same over here, everyone, if you would. From here, right on through the center, which in this case was at the origin. Same deal, just kind of like that. So see if you can get a couple asymptotes in there. We'll be modeling those asymptotes on the day 2 and day 3 of this, but that's a good start at least. So again, these hyperbolas fit within these diagonal asymptotes right here. You can see it on both ends. Nice. All right, let me go back to my screen that has the second piece. You're probably flipping forward and backward here, so keep it going if you would. It says, draw two tangent line segments that touch each vertex and end at the asymptotes. All right, so tangent line segments touching the vertex and end at each asymptote. See if I have that. All right, so guys, here are your vertices, one right here and one right here. So I want to go tangent to that and ending at each asymptote. So we're going to go dotted on this. Something like that, I believe, is what we're looking for. Try to get it perfectly, I guess, parallel to this y-axis if you get a chance. And then same here. I'm going to do the best I can. And not too bad. Could be better, could be worse. All right, so this is going to be an integral part of what we talk about. So we've got that piece, and I know what's coming, but let me go ahead and read what I have on that paper there. Here we go, number 3. Draw two perpendicular sides to form a rectangle. So when you do some graphing for me, and you'll be doing lots of graphing with these hyperbolas, one of the things you're going to have to draw is this little rectangle right there. And actually, this worked out pretty well for me. It could have been better just at the bottom, but not too bad. So that should be a perfect rectangle, and if you get an opportunity to put that in there, that would be great. And here's what I'm thinking. It's time to start labeling at least one or two things, and then I'll go back to my page and read some more directions. So should have potentially done this before, but I don't think we lose anything. From there to there, guys, is A. Center to vertex. Throw that in if you would. Let's go right below, and what do you say? Let's go center to focus. That's C. From there to there. Obviously, guys, you can kind of see what letter is missing, and so we needed to kind of draw a few other things in there to even talk about B. So let me go back to my other screen, so maybe we've got something going on. All right, let's go with this. So the line segment that passes through the center and is perpendicular to the transverse axis is called the, and here's your second piece, everybody, jot this in if you would, what's called the conjugate axis. So, just real quick, if you remember, in an ellipse we had the major axis and the minor axis. Kind of the major axis was 2A, the minor axis was 2B. Similar situation in the hyperbolas, but subtle differences. Sort of what would be the major is what's called the transverse axis, which is going to be 2A. And the other axis, we would call the minor axis, is called the conjugate axis, and its length would be 2B. And so let's go ahead and put this in. The distance from the center to the end point on that conjugate axis is B. Now, if you remember in an ellipse, we talked about the vertices and the covertices. Unfortunately, in the hyperbola, we don't have such a nice name like covertices or something like that. So we're just going to talk about it as endpoints on the conjugate axis. Not pleasant, but hey, it is what it is. All right, let's go on back. Let's do some labeling here. So real quick, if you need to, and I'm going to do this here, there's the transverse axis. So basically from vertex to vertex, length would be 2a. Hope everyone's cool with that piece. And by drawing this rectangle in place, we end up getting the secondary axis, and I'm going to go right there with it. And this would be the conjugate axis. So that is sort of endpoint to endpoint on the rectangle. That would be from here to here. Notice it's really nowhere on the hyperbola, so there's nothing we can really call it. It's just the endpoint on this axis. And we never labeled B, so let's label B. And so B is from here to here. All right, so there are finally your three letters in action. A, center to vertex. B, center to the endpoint on the conjugate axis. And C, center to focus. Nice. Shouldn't surprise you, but there happens to be a relationship with those three variables right there, and so I think that's what we're going to develop next. Let's just make sure. Hopefully everyone's all right at this stage. Again, these notes worksheets work out beautifully for something like this. So we just fill in and we try to learn from the investigations at hand. All right, so here's the big one. It says measure the distance from center to a focus, and then it says draw a line segment from A to B and measure the distance. All right, I hope you still have that ruler handy. That would be the ideal, of course. But here's what I'm thinking, everyone, if you would. Can you go for me center to focus? Just grab that ruler and just measure it as simple as it gets from there to there, whatever C is. Okay, everyone all right with that? You've got your ruler. You've given me a measurement. Just keep that in the back of your mind if you would. What is C in this diagram? Now, here's what I want you to do. Please go ahead and measure endpoint on the conjugate to the vertex, kind of like here and here, basically what would be the hypotenuse. Now, we'll see how you drew your rectangle, and it's tough for me to tell, although it looks pretty decent up here. But guys, let's go ahead and throw one more dotted line in. I'm going to go, there we go. That looks pretty good, all things considered. That's what I'm looking for. And, it shouldn't come as a great shock because I'm having you do both of these, but this distance right here, the C value, should be identical to here and here. So this is also C. And that's what I need you to put in. And how cool is that? Now we have our nice looking right triangle kind of right in there. We've got our A squared, we have our B squared, and now we've got our C squared in the right triangle. That looks great. Okay, so I think we're ready for it. So we'll talk a lot about compare and contrast with hyperbolas and ellipses. You see the relationship at hand, and obviously this is the big one right here. Just like in an ellipse, you probably use that C squared equals A squared minus B squared all the time, just probably on every problem. Probably very similar here. You're going to use this relationship in probably just about every problem. So this one is the more conventional Pythagorean theorem. C is the hypotenuse, so you've got that. So C squared is equal to A squared plus B squared. That looks great. All right, all the geometry is in place. I'm going to go back one time just to make sure if you're understanding everything here. That's awesome. We'll go ahead and get the algebra taken care of momentarily, but I think the geometry is pretty much taken care of at this point. The labeling looks good. Let's go with the two axes. One here, transverse axis, vertex to vertex, and then the conjugate axis, endpoint to endpoint. And then what we saw here is that center to focus is actually the same as this distance right here on that rectangle. And so as a result, we get a beautiful relationship between our three variables, A, B, and C. Okay, that looks really good. Let's move on. So it's definitely time. Let's put it on the coordinate plane. Find an equation. In this case, standard form. We're going to go center at the origin, and this will be horizontal first, and we're going to be a little careful here. Throughout the ellipse lessons, everybody, I kept saying the order in the fractions didn't matter because they were plus, right? When you add two things together, it doesn't matter, of course, in which way they're ordered. But what you're going to see here, everybody, with the hyperbola is it's two fractions with a subtraction symbol in between them. And yes, order does matter, obviously, when you subtract. So the horizontal, here's how it plays out. The x squared will go in front for horizontal, y squared will go on the back for vertical. Good? A squared underneath that. This is going to kind of give us our direction. This is only secondary, of course. And there's our b squared under that as well. And that's the first one. So if you remember an ellipse, it was just a plus. Here it's a minus. By just changing that one minor thing, you change it from a closed curve, being an ellipse, to an open curve, two branches of a hyperbola. All right, beautiful. Let's get this. Standard form. Let's do the vertical one. And center at the origin. And you could probably guess what's going to happen here. Let's get that taken care of. Two fractions, if you would, minus in between. And because it's vertical, this is how I'm going to know. The y squared is out in front. And going to the vertices, obviously, direction matters. The vertices are in the direction that it opens. And so A is, you think vertices with A. So that's why A is going to always be out in front. And x squared on the back, and b squared right there. And there you go. As I've said before, if you put the infinite number of ordered pairs into this equation and that make it true and plot those on the coordinate plane, it forms two branches of our hyperbola. All right. So before we kind of dive in with a couple examples and try to put this all together, I think it really benefits us to talk about some of the fundamental differences between an ellipse and a hyperbola. So these are the ones you just have to be careful of. Try not to overlap the two and try to keep them really segregated in your mind if you can. So I've got it down to about 3, and let's keep it simple to start. So hyperbola, minus for the hyperbola. So the two fractions, you have a minus in between. That's all. And plus for the ellipse. There's one pretty fundamental difference right there. Oops, let me get that in a little better for you. So minus for the hyperbola and plus for the ellipse. Right? So that's not too bad. Nice and straightforward to kind of start. To me, I think number 2 is the key. So I'll put a little asterisk next to this. And it all comes with looking at the equation and understanding which direction it opens, or in terms of an ellipse, which direction it's stretched. So here's the idea. For a hyperbola, it's the variable out in front. That's how you determine the direction of the hyperbola. So let me write this down and then we'll talk. So the variable in front determines the direction. That's the key. Not A and B, like in an ellipse. So let's talk through that one just real quick there. In an ellipse, we always said just look for the bigger number. The bigger number would be A. And then as a result, whichever letter it was under, that's how you determine the direction, right? That's in an ellipse. Not so in a hyperbola. In a hyperbola, it's just whichever variable is out in front. Let me just go back one screen, of course. So here's the deal. If x is out in front, it's horizontal. If y is out in front, it's vertical. That's the key. These, quite frankly, are irrelevant. We'll talk about one more difference in just a second there, but it's really this piece. Horizontal, x is in front. Vertical, y is in front. And that is definitely unlike what our description was in an ellipse. Okay, and then number 3, a squared and b squared. Unlike an ellipse, b squared can actually be bigger than a squared. It doesn't mean it will be, but it can be. So I'm going to go ahead and just underline that. So b squared can be bigger than a squared. In an ellipse, that's not the case. In an ellipse, a is always bigger than b. So just some real fundamental differences there that you're going to have to be dealing with. So think back to when we did the 3-day set on ellipses and really modeled that appropriately. And now, again, you've got to turn some of that on its head in order to work with the hyperbolas. Okay. Well, let's put it in action. Let's see what we can do. So example 1 is just a nice, straightforward one. Get us thinking about it. We're going to use this equation right here. Again, the infinite number of points that make this equation true form 2 branches of our hyperbola. And let's see if we can sketch that out and get a good sense of this. So here we go. Letter A. Does the hyperbola open vertically or horizontally? All right, right away. Let's think about this. And in this case, if I look carefully, because it's a hyperbola, and there's the hyperbola piece, it's minus instead of plus. Because of that, I know that this is what tells me the direction. Because the letter out in front is x, then we are talking horizontal. So that is our key. These 2 numbers right here are irrelevant in terms of the direction. They will help us sketch it, of course, but doesn't have anything to do with which way it opens. Only the variable out in front does. Okay, let's do this just as I'm thinking about it. We're doing center at the origin today. Obviously, on the next notes worksheet, we'll take the center off the origin, but for right now, we're good to go. Let's go ahead and get a couple things going here. So I don't know if I'm necessarily going to go in order. I'm just going to play it out how I normally would. And so let's do vertices. Let's get that first. So as soon as I hear the word vertices, I'm thinking A. Now in this case, remember the vertices go in the direction of the open. Always have, always will. So it opens horizontally, and so in this case, we kind of look to the horizontal piece. That's why A is always out in front, no matter which is bigger, which is smaller, doesn't matter. A is out in front. And so as a result, you notice I kept the numbers pretty easy for you. A is 4. And as we go ahead and sort of write our ordered pairs here and here, you know, obviously what we want to do is come off the center. In this case, the center is at the origin. And I should kind of put this right below here. Are we going up and down, or are we going left and right? And I'm hoping you would agree that we go left and right. Okay, so same direction as the opening, of course, to the vertices. So I literally just go 4, 1, 2, 3, 4, put a vertex. 1, 2, 3, 4, put a vertex. And so we have our 2, plus or minus 4, comma 0. Looks great. All right, now, next piece, I'm going to sort of skip C and go right to D here. Again, I wish we had a better name for it, like co-vertices, but we don't. They're not really vertices, so they're just endpoints of the conjugate axis. So I'll write that in there. If you guys want to do the same, that's great. If not, so be it. But let's go ahead and get that piece. So as soon as I'm talking about that, obviously, hey, we're talking B. And so B is always the back number. Notice it is bigger than A. Sometimes it is, sometimes it's not. It's just on the nature of the hyperbola. Okay, so B is 5. And just like we did before, if we went left, right to the vertices, we're going to go up and down to these endpoints. So if you would, 1, 2, 3, 4, 5, put a little x there. Again, it's not on the hyperbola, so we don't want to put it as a point. 1, 2, 3, 4, 5, same deal. That's looking pretty good. And just those endpoints, I saw one up at 0, 5 and one down at 0, negative 5. No harm done. Nice. What you saw when we looked at the hyperbola before, really on that front side, is that the rectangle is based on those values. So I'm going to actually start drawing my rectangle here, which will determine the boundaries for the branches of the hyperbola, because we're going to draw our asymptotes in momentarily. So something like that would do. Hope everyone's comfortable with that piece. And now what we want to do is Well, you know what? I think, again, I'm going to skip the foci for just a little bit. Let's sketch this. I think we have enough at this point in time, so we might as well go ahead and do a little damage here. Here's what I have. Here's our rectangle, I guess. So our asymptotes are going to go right on through the center and the corners on our rectangle. Something like that, give or take. And come on, let's get that in there. Oh, a little better. Something like that. Could have been better, could have been worse. And so the way the branches of our hyperbolas work is they each branch comes off the vertex, opening horizontally, and the arms of the hyperbola are going to get infinitely close. As they stretch outward, they're going to get infinitely close to these asymptotes, these boundaries right here. So when you get an opportunity, let's go ahead and do that. There we go, something like that. Something like that. Again, not too shabby. Got it up there. Good. And good. Nice. You see, really, the bend of the curve is quite a bit different than a parabola. And that's looking great. Nice. Okay. I do want to come back to that piece. I'm missing one little aspect of this. Even though the foci are not on the hyperbola, remember it's their position and the definition that really generate the shape of the hyperbola. So let's get that in place. In this case, you're just going to have to make sure you have the right equation. It is the straight up Pythagorean theorem as you know it. So c squared is a squared plus b squared. And so let's go ahead and, again, nice thing about this standard form, how great is that? They're right there. 16 is a squared. 25 is b squared. I'm getting a c squared is 41. Undo the square right there. If you want to do a plus or minus, that's perfectly fine. That's your call. Obviously, it is one to the left, one to the right. And here's the question with those foci as I solve for c. So c is equal to square root of 41. And I guess the question, of course, is up, down, or left, right? And if you've kind of been following along so far, I'm hoping you're in agreement. It's left, right. Just past that transverse axis, of course. And that looks perfect. So left, right here, which means we're changing the x. How does root 41 comma 0 sound? And negative root 41 comma 0 sound. That all right to you? And if you want to go ahead and grab a calculator, whatever square root of 41 is, I'm assuming just kind of about 6.4-ish, give or take, somewhere in there. So let's see, 1, 2, 3, 4, 5, 6, and just a touch. What do you say we go ahead and put that in? Same here, 1, 2, 3, 4, 5, 6, and just a touch. Something like that. There are your two foci. All right, one last thing I'll ask of you, and then we'll do the last problem here. Pick any point on either branch of the hyperbola. Makes no difference. Just to illustrate. And if you would, go to one focus. Go to the other focus. Now picture yourself subtracting these two distances. This minus this. Kind of take this away from this whole thing right up here. Would that be constant anywhere at all on either branch of the hyperbola? Yeah. And that's the case. Sorry, I'm going to go on back just one time thinking about it. There it is. Again, the difference of the distances is constant. Cool. All right. Sorry about that. Just needed a breather for a moment. Thought I'd bring that up. All right, last one there. Example 2. Find the equation of a hyperbola with foci at 0 plus or minus 3 and vertices at 0 plus or minus 2. I hope you're all in agreement. Just looking at that, and obviously that's the highlight for today, is that the center is at the origin. So let's throw that in place, if you would. Center right at 0, 0. Obviously right in between the two foci and right in between the two vertices. Not a big deal. And let's go ahead and throw our A, our B, and our C in. Hoping you're looking at that right away. You know that C is going to be 3, center to each focus. And an A looks to be 2, center to each vertex. And notice difference between an ellipse and a hyperbola In an ellipse, the foci are inside, so C is always smaller than A. But in a hyperbola, obviously, C is larger than A. Kind of cool. All right, well, let's go get B. You know it's coming if we're going to write the equation. Really, we just need B squared, but whatever. If you want to get B and put that in, you're more than welcome to. So let's see. C squared is 9. A squared is 4. B squared is missing. Hoping you see we bring the 4 on over. And looks to be B squared is just the 9 minus 4, which is 5. And that's what we need. If you want to go ahead and square root, then B is obviously root 5, but that's sort of irrelevant. I think we could knock this out here in the next 30 seconds. Would love to see you pull this off. I set up the template. You guys fill in the information, but I think we have it all. Remember, just be careful on this. With the minus, it now matters which is out in front and which is on the back. So, here's what I have. I know it's the y out in front because we're going from the center to each of the vertices and the foci. We're going vertically to do that. We're going up and down. So it's opening vertically, and so y out in front, x on the back. So I hope everybody did that first and foremost. And in this case, remember, if we're going vertical to those vertices, vertices, you think A, and so A squared is always out in front. There's your 4. B squared, then, is always on the back. And there you have it. There's your equation. And that should pretty much round out day 1 of hyperbolas. You can see it takes a little time to develop some of the geometry there. And then the algebra comes in nicely on top of that. Some great stuff. All right, get used to some of these pieces, and again, try to segregate, if you could, all the stuff you did for ellipses and now all the stuff you're going to have to do for hyperbolas. There's some subtle differences that you're going to need to be aware of. Hey, as usual, thanks for listening, and let me know if you have some questions along the way.